video on electronics for preliminary or Year 11 HSC engineering studies. In the previous video, the last thing I left on was we were talking about the difference between series and parallel circuits. So series and parallel circuits, we talk about how they give different resistances depending on, if we have, in this case here, three resistors in a straight line will have more resistance than three resistors that are bundled up like this. Now, you should be familiar with this at some level from junior science, but the idea is that if they're in a straight line, we call that in series, and if they're each in a separate line like this, we call that parallel. The biggest things to know is that if in series, if one part of this system fails, if the first one fails, the whole thing fails. And so this is where often with Christmas lights were often wired in series to reduce cost. These days, I believe that even modern Christmas lights, they're still wired in parallel as well, because the cost of returns when a light blew, that very few people would want to replace them and would want to replace the individual globe, figure out which globe was busted, so they now wire them in parallel as well. The big advantage as well is that by wiring in parallel, we get a energy efficiency. So I'm not going to go into this here. What I'll say is that I do go through past HSC questions, and I use these to explain the difference. That if we look at this, here we have a 9-volt battery, and we have three 12-ohm resistors in this circuit. We're going to have a current of 1/4 of an amp, whereas if we have those same three 12-ohm resistors, but they're in parallel, the difference is we're going to get 2.25 amps. So that's an increase of more than 10, 11 times, something like that. So that's where we left off with series and parallel. So that takes me back to the textbook, not that textbook, where we talked about simple circuits. Simple circuits can be either in series or in parallel. So convention states electricity flows from positive to negative. However, electricity is the flow of electrons, which are negative particles, so in real life it flows the other way. So what we use is the term current, which is opposite to the flow of electrons. Like I said, they do talk about that in this Magna Guide to electricity, but it might be in past chapter 1. I have focused on the part that I'm interested in. So there's two areas that we can go to from here, or maybe three areas. We can talk about electrical generation, we can talk about power, we can talk about semiconductors, or we can talk about electrical safety. Any preferences?
Electrical safety.
Excellent. Well, that was actually the one I was going to go to anyway. Electrical safety is the next one in the book. Maybe that was an influencing part of your thought. Okay, so electricity can be considered lazy, or it travels the path of the least resistance. This means that people have high levels of resistance. Our skin typically has high resistance. So given the choice, electricity will run through a metal wire rather than running through a person. So there are situations, though, where the electricity has no other path than to go through a person. Now, although we say that electricity will rather go through electrical wire than go through a person, if the electricity has to return all the way back to the power plant, well, it's a long way back to the power plant. And instead of going to the power plant, where it can go instead is it can go to the ground. And the ground is very close. And if you are the thing that's joining the electricity to the ground, and it can choose between going through you to the ground or going through all the way back to the power plant, it might just choose to go through you. Now, there are things... Well, if you're jumping, then no, because you're not connected to the ground. So, but eventually, if you come to... If you were able to time the... look, I don't want to say this as an authority, but I'm pretty sure you would be able to jump and not be connected to the ground. Also, things like if you're standing on a wooden chair, because wood doesn't conduct electricity, timber chair doesn't conduct electricity. if you're standing on something made out of plastic, or if you have really thick rubber-soled shoes, these are all things that can help you and help electricians when they work with electricity to not be electrocuted. But electricity does kill people. It kills people every year. And we have to take precautions to prevent people from being killed by electricity. It only takes a very small amount of current. They say less than 1 amp is enough to kill people. We will cover that in a second. But let's see what Copeland has to say. So what we do is we don't want to touch the wires, right? We generally, as a general rule, we don't want to touch the wires. So what we do is we cover all wires with at least one coating of plastic, and typically with several layers of plastic. So there's plastic coatings within plastic coatings. So that if any of you have ever seen a cut wire and seen how there's little wires inside it, and each of those wires is separately coated, there's reasons for that. The reason why they're separately coated is because in order to maintain that parallel circuit, we need to have at least 2 wires in the cable. And often, when we see PowerPoints, we can have 2 pins in our PowerPoints, or we can have 3 pins in our PowerPoints. So that's a choice that we can look at. So let's have a look. What we've got here. As a consequence, we're designed. Okay, we cover the live wires with plastic. Then, if something has a metal surface, appliances are either earthed if they have a metal surface. So if something is made out of metal, it has to have an earth. We'll talk about that in a second. Or they can be double insulated using polymers to prevent shock. Earthing means we're going to talk about that in more detail. Modern domestic appliances are often double insulated. Okay, we'll talk about that. In addition to that, there's now safety switches, also known as residual current devices, RCDs, to prevent earth leak. I put a question about that in my last year's preliminary exam, and some people disputed whether or not we had discussed it. So let me say here, safety switches are also known as residual current devices, and consider yourself warned. And we've already talked about Australian standards when we talked about communications. So Standards Australia, they specify standards for a lot of things, and we are going to cover that. Okay, so back we go to our thing, and so we're going to go to our safety. Okay, I'm going to put on a song called So when I went to Leon with my friend Disco, he lived in a dorm while he was there, and the dorm had a little piece of paper where you could. It's got a bit of a weird film clip, so I might tab out before I. He had a little spot where you could put a piece of paper where you could put your name. And I thought it would be funny while he was away to put in that piece of paper discotheque, which is French for disco. And I thought that was funny. And later someone set fire to that piece of paper. Like fire in the disco. Anyway, so yeah, so this song starts with the line, fire in the disco. Anyway. So, danger high voltage is our picture for electrical safety. What are we going to learn about? We're going to learn about earthing. We're going to learn about circuit breakers, fuses, safety switches, double insulation, shielding, and compressed air. So, quite a lot here in my electrical safety. Okay, to start us off with, well, when you cut open your electrical wire, you might see 3 colored wires inside the cable. So I believe when I did work experience with an electrician, I believe they call this cable, and inside the cable are wires, is the specific definition. But, don't quote me. Outside my area of expertise. Okay, so what I have here is, this I think I got from Wikipedia, is the colors of the wires. Now, what we can have is we can have in the in Argentina, the EU, and South Africa, and in Australia and New Zealand, they use different standards. America, different standards again, so they're a little bit more confusing. But what we have is we can have brown for the live, the phases. So if we have 3 phases, we might have multiple colors, but the electricity that's coming into the house runs on the red or the danger wire. Yeah, it's to warn you that there's danger. And then the return, the cable that takes the electricity back to base, is black. Is blue. So we can see previously when I first learned electricity. So the Australian standard is 3000, and it was updated in 2007. When I learned about this earlier in the early 2000s, it used to be red, black, and green, and now it complies with the EU convention, which is brown for the live, blue for the return, and green and yellow stripes for the earth. So that's what we can see. That's our standard, is that brown is the live, blue is the return or the neutral, and red and green is the earth. Now, the blue is not necessarily less, I mean, theoretically it should be less dangerous, but I would not count on it being less dangerous. So I'm putting that out there. Okay. I'll just put the saxophone solo on for a sec. Okay, so now that we know there's 3 different wires, well, what does this earth wire do? Well, often what there'll be a pipe somewhere near the side of your house, often connected to mains pipes, so your water pipe. And so plumbers often have to be very mindful of this, is that there is a there is an earth wire that connects your house to all of these yellow and green wires. And so the idea there is, remember we said before that the electricity has to go a very long way to go back to the power plant to complete that circuit. I've clearly been playing a lot of Electric Dreams recently, so that's why that one's come on. I probably could have left it on, but anyway. So in order to shorten the distance the electricity has to go, well, remember the electricity just wants to go to an area that doesn't have many electrons. What we do in a generator is we create one side of the circuit that has lots of electrons and another side of the circuit that doesn't have electrons, but has a shortage of electrons, it has a positive charge. Well, the ground, the earth, the stuff that we walk on, it has, relatively speaking, a very positive charge compared to the electrical generator. So the electricity is very happy to end its run and say, you know what, I can't go all the way back to the power plant. I'd much rather just go to the ground instead and release the charge into the earth. And because it's so far away to the power plant, it's just happy to go instead to the earth. Now it can go through the earth through you, or instead, if you give it the option, it would happily go through the earth through this copper wire. Now it's a lot faster to go through the earth wire, the grounding wire, than it is to go through you, because like we said before, you're not very conductive. We can be more conductive if you're sweaty or if you're wet, if you've just had a shower, if it's raining, all those sorts of things make you more conductive. There are different considerations that make you more conductive, but generally speaking, given the opportunity, electricity, so if you have a frayed wire and if you touch a frayed wire, well, if that electricity, or let's say if you touch an object that has a frayed wire, the electricity would rather go through the earth wire than through you. I guess that's sufficient for me to say here. Now, I've used the term earthing and grounding, and that's what I have open here, is to a YouTube video, which I'm not going to go into because it's definitely beyond my level, but it does specify that there is a slight difference between earthing and grounding, but as far as I'm concerned, in a Year 11 or Year 12 course, I'm happy to accept that for the moment, earthing and grounding, same thing. Okay, so the next thing we're going to talk about is the tag and tester course. So I, at some point in my life, thought it would be a good idea to do this course. It cost me a couple $100. And if you buy this machine, you can go around and you can tag electrical equipment. Most people don't tag electrical equipment in their home, but it's usually a condition of most workplaces that they have tags on all of their electrical devices. When you go to school next, pay attention if you look, every single cable should have a tag on it. It should say when it was tested and who tested it, and it will have a reference to say that this has been tested as being safe. Now, without going into too much detail of the course, like Copeland said, if the object has a metal surface, it has to have 3 pins. It has to have that earth pin. But a lot of things, especially things that come from America, they don't have 3 pins. Instead, they only have 2 pins. And if you have 2 pins, it needs to be covered in plastic. It can't have any metal surface that you can touch. A comment that I often make about this is that right now I have my laptop plugged into a cable. I'm just holding this up. And you can see this cable, it has, this one here, it has 3 pins. This cable, okay, so for people who can't see literally what I'm holding up my MacBook charger, and the thin cable to the left, well, it maybe can have 2 or 3 pins, but the thick cable to the right, it has 3 pins, because this cable here has to be safe. Because it's carrying 240 volts, it has to have an earth pin. Whereas if I take this off, MacBooks, you can take off the long cable and replace it with the little plug. And when you replace that with the little plug, it only has 2 pins. So what I've learned is if you're ever going to America or China, China theoretically should use the same plugs as Australia, but because they're pretty accommodating actually, but in some places they won't have a capacity to take 3 pins. So if you buy a adapter for an American outlet, you might want to take out that long plug and replace it with the small plug that they give you, so that way you can plug it into your US adapter charger. Yeah, so just a tip for you. I'll show, if I remember, I'll bring in a US adapter, and you'll see that it can't take a 3-plug appliance because it only wants to take 2 plugs. You can buy a 3-pin plug, but that won't go in a lot of plugs in the United States. So it's a bit of a tough one. So whenever I travel, I get rid of that long plug and I replace it. A quick tip that I'll give anyone who's going overseas: take a power board with you, because it gives you like way more power outlets for your adapter. Does that make sense? Yeah, great. Okay. So the next thing is the concept of shielding. So when we're talking about high voltage, danger, high voltage. When we're talking about high voltage cables, so this here is, well, how many volts do we use in Australia? 500. Nope. Well, okay, it does vary. So in this this manga guide to electricity, you can see somewhere in all this Japanese that's written around that they talk about that they use, what is their voltage that they use out of the walls? I think they use 100, like it's 100 volts here. Yeah, I think they use 100 volts, where America uses like I think 110 volts. Europe uses 210, 220, I think, something like that. Australia uses 240 volts. Now, when we create the voltage, it doesn't come out of the power plant at 100 volts or 200 volts. Instead, what happens is it comes out of the power plant at tens of thousands of volts. So here we can see this is a 400,000 volt point. If you have 3-phase, I think 3-phase is 415 volts from memory. But if I'm wrong, I'm going to check that. Close to 400. 415. There we go. So, like for instance, the machinery that we use in the woodwork room, that will all be running on 3-phase, and that has a different power point. Caravans, they will have a different power point as well. Let me show you that, a 3-phase plug. So a 3-phase plug looks different to your regular output, your regular plug, and So anyway, it comes out of the power plant at hundreds of thousands of volts, and then it travels through those big transmission lines we saw earlier when we were talking about aluminium to utility pole transmitters, and so substation transformers, and then to the utility pole transformers, or sometimes you might see little green boxes around your street. I used to point these out to my kids when they were little. I don't know if I've done that recently. So you might see big transformers. Okay, so you might see, I'm just trying to think. We're near my kid's grandparents' house, so near my grandparents' house, my grandmother's house. There is a block of land that is just filled with electrical equipment. So that's a local area substation. But then we have little substations with transformers in them, and these can just be around. They might be on the street near your home, and they're smaller substations with transformers in them. And so transformers change the voltage. You may also be familiar with the Michael Bay, Shia LaBeouf and Megan Fox movie, where with transformers. Anyway, but assuming that the point is that transformers also used in electricity to talk about things that change the voltages. So the stuff that is traveling from the substation will be going at huge voltages, hundreds of thousands of volts potentially. And then when they get down to the substation transformers, so for instance, when I used to work in rail, we used to work a lot with the HV, the high voltage lines, and then we would drop that down for the train to use itself. So I think the trains run on 450, but then the high voltage power lines, they would carry 33,000 volts, 33 kV. So I think that would probably be these ones here. From here to there is 33 kV, and then this brings it down to 415, and then at the house it comes down to 240. Okay, and then it goes to a distribution board, and in the distribution board, this is what distribution boards used to look like. I'll show you a video in a second of what more modern ones look like. I mean, it's not using fuses. This is still using circuit breakers, so it's could be older. There we go, circuit breakers, and a current limiter, which is another term I think. So the leakage circuit breaker is another term for a residual current device. Okay, so what they're going to talk about is that if this girl I can't remember her name, if she has the tea kettle and she has the rice cooker on at the same time, it's too many amps, right? 20 amps, too many amps. And there's a reason why Zoa, there you go, that's her name. Zoa has not... okay, so you can't plug in everything at the same time. You can't plug in... you can't have everything running at the same time, because otherwise it might trip your circuit breaker. The reason why we do that is for two reasons. One is for safety, because we're going to talk about how many amps it takes to kill you. So for safety, the circuit breaker does not exceed 20 amps. And but if you plug in something else, the other reason why we don't want to be there is so that it doesn't damage the circuitry, because too much current can destroy things. If anyone's ever watched Star Trek, whenever they get hit by the pulses, people talk about how everything catches on fire because in the future, for some reason, they don't use fuses. Anyway, or circuit breakers. So let's go back to our thing here. So in the case of very high voltage, what we have here is we have, I think the live is on the inside. So the current that's leaving from the power plant, that's on the inside. And that core might just be for stability. And then we have a huge insulator. And then the outside, we have the return wire, the neutral, and then we have another insulator around that. So that way, if something happens, if someone cuts into the wire, well, yes, it's dangerous because we've said that the return or the neutral can still be dangerous, but they're not cutting. They have to cut all the way, or they have to cut halfway through the wires until they can get to the very high voltages. Okay, so then we have residual current devices, RCDs. Which are also known as safety switches, or what do they call them? Current leakage devices. Current leakage detection, maybe? Was that what it was called? The leakage circuit breaker. I'll just check that is, in fact, no one wants to be wrong on the internet, better to search. What was it called? Leakage circuit breaker. An ELCB is a safety device. Once widely used, more recent installations instead use RCDs, residual current devices. So there is a slight difference, but yeah, these days we use RCDs. And I'll post that here. Okay, so let's have a look at what our modern distribution board looks like. Well, it's worth talking about, before we had our modern distribution board, what does an even older distribution board look like? And so to find that, what we're going to try and do is we're going to try and find a picture of fuses. Oh, I've got some down the bottom. Okay. So this is what we used to use. I remember my dad, when I was really little, changing a fuse when we must have overloaded our circuits. And so what happens here is that, let's see if I can get a better picture of that. There is a thin wire that someone just manually winds around this piece of ceramic. Yeah? And the electricity is conducted through this wire. And if there's too much if there's too much current through the wire is thin enough that it melts. And when it melts, you then go out, you figure out, you look at all your fuses, you figure out which one's melted, and then you take some fuse wire and you replace it. Now, that wasn't particularly convenient, and the biggest problem is that sometimes it was quite dangerous. So what people would do, if you were lazy, right now, I want to specify here, this is really dangerous and you should not do this. This kills people, this kills particularly electricians. What people would do is they would just replace the fuse wire with a piece of copper wire. And obviously the copper wire, it's not going to melt, right? So effectively they're just bypassing the fuse. There is no fuse. So it means that there's no current protection, nothing that's limiting the current in your house. It starts fires and it electrocutes people. Now, it's worth mentioning that an electrocution means you're dead, right? It comes from the word execution, electrocution and execution, right? It's a portmanteau of electric execution. If we're instead talking, oh dear, I needed that window open. If we're talking about a non-fatal burst of electricity, we call that electric shock. Can I go back to my... Oh, there it is. I couldn't see the arrow because the recording is covering it. Back you go. Okay, so this setup's probably using more power even than the Word application. Okay, so Microsoft Word. Okay, so what are we looking at? Well, so we've now seen that fuses have been replaced with circuit breakers. Again, I had this in a question for my preliminary students last year, and they were upset about this. That they said, don't houses use fuses? And I said, not modern houses. And I'd specified in the question, a new home construction will be protected by earthing. So a new home construction will be protected by earthing. It'll be protected by a circuit breaker, and it will be protected by an RCD, or a residual current device. Okay, so what are we looking at here? We're talking about fuses. Before I move on from fuses, we do still use fuses. Cars still use fuses. So that if you have an electrical surge, let's say your car gets hit by lightning, right? Can happen. If your car is the tallest thing in the area, then electricity, it doesn't want to go through air because air is not a good conductor. It sees your metal car and says, I'll go through that. Now, it does have to go through the rubber of the tires, but it would much rather go through the 200 mil from the bottom of your car to the ground than the 2 meters from the top of your car. I mean, maybe if it's going through an antenna back in the old days. Or anyway, moving on. The point is, your car has fuses to, and I'll, anyway, your car has fuses that protect your car in the case of an electrical surge, and these things will melt if something happens. If your car gets hit by electricity, these will melt to protect your car's computer systems from so most people these days don't have your modern cars don't have carburetors. They have computer fuel injection, and you have like your CD player. My daughter was once when we got a new car, she was upset that we didn't have the music on, and she didn't have the Bluetooth, and she said, what's the point of having a nice car if you can't even listen to your own music? Anyway, so if you can't protect your electrical equipment, that could be bad. Usually fuses are brightly colored so that you know how many ohms you need, or how many. I think it's measured not in ohms. It's measured in they're rated for amps, and you can get these ones, which I used to think were pretty cool when I was a kid. I think these are older, and my Lego men used to play with them, and I used to pretend that they were the ooze from Ninja Turtles. Anyway, a little bit of puns trivia for you. Okay, so let's go back to RCDs and circuit breakers, our modern home safety setup. Okay, so fuses and safety switches and circuits, they do different things. So here we have the Queensland government explaining that there is a difference and why we want to have both. And what they're explaining is that the purpose of a safety switch, so in the circuit breaker is when there's excessive current. What happens is the safety switch has a computer, and it can detect if the amount of electricity coming into the house is substantially different than the amount of electricity coming out of the house. And so if it says, hey, I sent you 200 volts and I'm only getting 40 volts, where did the missing 160 volts go? Well, the safety switch doesn't wait for an answer. It just switches off, because it does not want that current to go through a person. What it's suggesting is, hey, we've leaked electricity here, we've leaked current, and we want, so the circuit breaker might still allow it, but when we have, so circuit breakers trigger when there's too much current being drawn, right? So there's too much current in so say electricity hitting it, the circuit breaker switches off switches off the electricity to the home to stop a surge, an electrical surge, or from devices using too much power. Whereas a safety switch is a computer that will detect whether or not there is a leakage in electricity, and this is what they're designed. Both of them serve a purpose in saving lives, but safety switches, and this tells you how to reset a safety switch. There could be this T button to test them. Anyway, it's a worthwhile video. I remember watching it and thinking it was fine. What's the difference between a circuit breaker and a safety switch? This is the same. This uses a lot of the same resources, and I think it's a good written explanation of what's the difference. And here, this is the modern circuit board, and it shows you how to reset them if they trip. So if you get there and you find that there's no power, and you see one of the switches in the wrong position, if you flip that switch, now if that switch goes straight back down, as soon as you lift it up, if it goes back down, well, that means that you need to unplug the devices that are on that fuse or on that circuit breaker. How do circuit breakers work? Well, here it goes. Fuse box keeps tripping. So you've got to go through and figure out what is the device. It might be your slow cooker. Last year, our slow cooker kept tripping our circuit board, and living in the age of disposable products, I was going to throw it out, but we were able to fix it, and it doesn't trip the switches anymore. Okay, so residual current devices, RCDs, operate by measuring the current balance between the two conductors between the different current transformer. This measures the difference between the current flowing through the live conductor and that returning through the neutral conductor. These, if they do not equal zero, if they're not perfectly balanced, it means that there's electricity being leaked somewhere else, and it will then open the contacts, which means it shuts off. I probably should have had a more simplified answer there. Okay, we've talked. Okay, so what we want would be great is how circuit breakers work. Do I have that? Okay, how circuit breakers work is through thermal expansion. How So they use, okay, so let's have a look here. Okay, great. Basic design. There was no picture earlier, so I was concerned. Okay, so with a fuse, it disintegrates. The basic circuit breaker consists of a switch and a bimetallic strip. There we go, that's what I was looking for. So a bimetallic strip, you may have learned about these in science. The idea is that we can have switches that turn off at a certain temperature by having two metals. And if we have two metals next to each other, let's say, just for the sake of argument, we use a steel and copper, right? Steel is subject to corrosion, but let's say steel and copper. One of those two is going to expand more under heat. They won't expand at the same rate. And when one expands more, they're going to bend. And when they bend, it's going to touch the contact and it's going to switch off. Or it's going to pull away and so no longer conduct electricity. So that's when they talk about a bimetallic strip. The thermal expansion causes the thing to pull apart, or it can work on an electromagnet, whereas they're saying that the modern ones, they use a semiconductor. They use basically a small computer that measures the current. It just has like an ammeter in there, and it reads the values on the ammeter, and they're more reliable. They work with much lower, they work much more accurately, but they're more expensive. Okay, so I will still cover that. I will still copy that rather in... because I think it's probably worthwhile. Okay, so worth pointing out that one of the things, when we talk about the hierarchy of control, so I think it was Harvard Business School was one of the real innovators in using this idea of the hierarchy of control, these 5 steps to reduce hazards. And this has now been adopted by everyone. And so there's the 5 steps in reducing hazards are, first of all, eliminate the hazard. So just don't do that job. The second thing is that if you can't eliminate it, substitute it for something safer. The next thing is if you can't substitute it for something safer, then you should put up physical barriers to protect people. If you can't put up a physical barrier, you should have rules, so administrative controls. And then if you can't just rely on rules, if you have to do it, then you should wear safety equipment. Now, safety equipment is considered the least safety component. What we can look at here is if we're working on a building site, rather than having electrical wires out in the open, in the rain, over puddles, there's things we can do. We can use physical barriers to keep those electrical cables high up off the ground, out of puddles. We can have rules on what you're supposed to do when you see the way that you're supposed to connect your power equipment, all this sort of stuff. But probably what is better, if we move up the order of the hierarchy of control, is we're better off using a substitution, which is if we can use, instead of using electrical power tools, if we can use air-powered tools, so things that run on compressed air, well then we have no electricity to worry about. Now, it's not to say that we're not eliminating the problem. We still have some risks of having nail guns and drills. They can still do damage to people, but what we're doing is we're substituting the problem for a less dangerous problem. So we're using air instead. Okay, so a quick thing on standards. So the AS 3820 or AS3820, it specifies all electrical equipment, what they need to have. So if you're selling a toy robot, it will specify if it plugs into the wall. Let's say an alarm clock. That's probably a better example. If that alarm clock plugs into the wall, it will have to comply with the AS3820. And if you're an electrician, now they don't specify electricians. They say instead a knowledgeable person. So electricity can only be worked on by a knowledgeable person. Now, that generally is interpreted under the law as being an electrician, but it can be, in some circumstances, say another specialty technician who has electrical training, or it could be someone like an electrical engineer, something like that. But for us, we're just going to say, don't play around with electricity. Builders, anyone with a builder's license, they can work on everything except the plumbing and the electricity. So I found this silly joke. I caught my son chewing on electrical cords, so I had to ground him. He was resistant at first, but he's doing better currently, and now he's conducting himself properly. Do you like it? Yeah. Anyway. As a student correctly identified, don't have a son. Okay, I don't know why blue LEDs is in this section. Blue LEDs, they're LEDs are semiconductors, so they should be in the conductor section. So that's in the wrong spot for that. Is there anything else I wanted to talk about with electrical safety? I think we've covered everything. We've talked about earthing and grounding. We've talked about circuit breakers. We've talked about fuses. We've talked about safety switches. You know what? I'm just going to chuck in here RCD. Double insulation, shielding, and compressed air. So we've talked about those things. Okay. So we have three things to talk about. We can talk about semiconductors, or we can talk about power generation. And if we're going to talk about power generation, we probably have to talk about power. I got the power. This is, yeah, well, I mean, always a good opportunity to talk about snap and the power. Okay, we're back here. Yeah, so I chose that one rather than Kanye. I do really like Kanye's Power. Last year, Triple J did the hottest 100 of the 2010s, and I was very irritated that Power came in at, like, Kanye's Power came in at like number 70, and then I gave a commentary of what I thought of every song that came on after Power, and I gave it a rating as how good it was compared to the song Power. I'm not saying Power is the best song ever, but I'm just saying it was a hell of a lot. It was much better than 77. Well, I'm not going to say 77 of those songs, but it was better than a good 70 of those 77 songs. Okay, so when we're talking about power, as we see up here, power can be measured as power is work over time. So then we have to talk about, well, what's work? If power is work over time, well, what's work? We have talked about work. when we when we watched the Eureka videos on simple machines, we said that work and energy are the same thing. Energy is the ability to do work. So if I eat food and I get energy, what do I get? What unit of measurement do I use? Joules. I'd have to do some finding to find my picture of Drake. There we go. Drake says calories with a capital C. No, kilojoules. And even Kondo, she likes kilojoules. Anyway, so we're going back to the power. So power is, what I want to find is this document here. Power is, we now know, is measured in joules. If you eat a donut, it's got about 600,000 joules or 600 kilojoules. We talk about kinetic energy in joules. We talk about potential energy in joules. We measure work in joules. So work is W equals Fs. So the where this ties in with Drake is somewhere I have Drake singing "Work, Work, 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 Work" with Rihanna. Okay, so what is work? What is work? Yeah, no, energy is the ability to do work, but what is work? What's the formula for work? Louder than I thought it would be. Force times distance, not mass times distance, force times distance. Is that what you said? Great, good work. Do you see what I did there? Good work, work, work. Anyway, I had to spell it out. Okay, so work, it is also the change in energy, but so there's complicated formulas we can use where we talk about the change in energy, but yeah, normally it's force times distance. So the idea is that if I have an object that has a weight of 1 Newton, so let's say it's a 100-gram apple, and I lift that up 1 meter into the air, how much work have I done? So 1 meter times 1 Newton is 1 joule. So how many, to just burn off 1 kilojoule, how many apples will I have to lift into the air? 1,000. Yeah. So if one apple 1 meter into the air is 1 joule, I'd have to do it 1,000 times for one kilojoule, right? And so to eat an apple, right, I'd have to do it 600,000 times. Now the reality is that my arm probably weighs a few kilos, right? Probably weighs, say, 3 to 5 kilos. Let's say it's 3 kilos. So if it's 3 kilos, that means my arm has a mass of 3 kilos, which means to lift it up into the air, I would be moving a weight of 30 newtons, right? So it would be 31 newtons with the apple. So I wouldn't have to do it quite as many times because my arm would be doing some of the work. Work. Sorry? Still have to do a lot. Just as a sake of argument, there's a saying that abs are made in the kitchen, and the idea is that if you want to lose weight, you really need to lose weight by not eating as much. A guy called Michael Mobbs had a documentary called The Truth About Exercise. Michael Mosley, there we go, not Michael Mobbs. You can watch this on Vimeo. And he talks about, he is a proponent for HIIT, high interval intensive training. So high intensity interval training. So the idea is, rather than running 2 or 3 kilometers, you're probably better off, especially if you're going to run 2 or 3 kilometers twice a week, you're probably better off running up and down 10 flights of stairs and doing that every day. That's probably a better workout for you because it gives you the health benefits of exercise for a smaller time commitment. Whereas what he found is that majority of the people who, when they do exercise, they will reward themselves with a Gatorade, and they'll just completely undo all the benefit that they had from that exercise. If they, the alternative is that they'll do a little bit of exercise, and then they'll be much less energetic at a very, very low level. He records, like, say, waitresses and waiters, that they do lots and lots of exercise because they're walking back and forth all the time. Whereas if someone who works in an office, if they do a lot of exercise, they will tend to be less energetic when they're at the office, and that also undermines their weight loss. My brother, the doctor, he on the other hand, he is on what we call the Steve Monaghetti diet. I saw Steve Monaghetti, an Australian. I saw Steve Monaghetti being interviewed on Australian TV at one point, and he said his diet was eat whatever you want, run 20 Ks a day, and that's pretty much what my brother does. He doesn't want to run 20 Ks every day, but whenever he feels like he's getting a bit overweight, he just goes for a 20K run. He's incapable of doing a 2 or 3K run, and when you're running that sort of distance, yes, you will lose weight. But the amount of exercise most people do. If you want to get some extra calories, now we just talked about how Drake doesn't like calories. You get pretty much for every kilometer you run, you get 1 kilogram for your weight. So let's say your weight is, for the sake of argument, 80. Let's say 70 kilos, right? You're a young fit person. You're 70 kilograms in weight, and you run 1 kilometer. Well, what you're going to be doing is multiplying that by 4.2. And that's going to give you, because 4.2 is to convert calories into kilojoules to make Drake happy, that's going to be 300 kilojoules. We said that a donut was 600, right? So you have to run 2 kilometers to eat a donut. Now, I remember talking to my kids once when I used to make them go running, and I said to them, what would you rather do? Would you rather have a donut and run 2 kilometers or eat no donut? The answer was always eat no donut. So some people really love running. Some people get that hormonal rush, that they get a chemical benefit from running, and the exercise makes them feel good. They say that if you're depressed, the very best thing for you is exercise. They also say exercise improves sleep, which improves your study habits. It has a lot of benefits. I'm definitely not saying you don't exercise, but according to that Michael Mosley was he's a doctor. He has a medical degree, and then he was also the journalist who first worked with the Western Australians to talk about how ulcers were caused by bacteria and not by stress. Bacteria, and not by stress. And that was like Nobel Prize winning work, I'm pretty sure. So yeah, he has like a long pedigree of being a well-respected medical journalist. He's not just some hack. He's not a Paleo Pete. Shots fired, Paleo Pete. Okay. So the point is, we've talked about work is measured in kilojoules or just regular joules, and we've then said that power, right? If we will go to Kanye now. 77th best song of the decade. This is not the usual film clip. I'm not sure what's going on here. Good censoring, because that would have been awkward. I would have had to have edited, and I hate editing. Okay, so power is equal to work divided by time. The power of a machine, or the power of something, is how many kilojoules you can spend each second. And in the case of electricity, well, power can be written as pi. We don't have it written as pi here, so that's confusing. Why isn't it written as pi? Why is it written as something crazy? Well, we have to go way back to Scranton, the Electric City, where I have this diagram. And remember I said I'd come back to this? Power equals I times V. And if we use M&M's E, right, that power equals pi. Power equals current times voltage, or power equals current times electromotive force. But there's other ways we could write it. Power equals I squared times R. Yeah, so we have all these different ways of writing it. What we're going to look at here is that they're going to use pi, or PIV, and they're looking at the side of the kettle. Now have a look, maybe your kettle has a sticker on it like this, or maybe your rice cooker, if you have a rice cooker, has a sticker on it like this. And what it says is, well, this runs on 100 volts, and how many amps does it draw? 10 amps. So, and then how many watts does it use? Well, we haven't talked about watts. What's a watt? Okay, well, so this is time for my, the video that everyone hates.
second? I don't know who's on third.
That's what I want to find out, the guy's name. That's what I want to find out, the guy's name.
I'm telling you, who's on first? What's on second? I don't know who's on third.
You want to be the manager of the baseball team?
Yes.
You know the guy's name?
Well, I should.
Well, you tell me the guy's name's on a baseball
I
team.
say, who's on first? What's on second? I don't know who's on third.
You ain't saying nothing to me yet. Go ahead and tell me.
I'm telling you.
You ain't saying nothing yet. Go ahead and tell me.
Who's on first? What's on second? I don't know who's on third.
You know the guy's name's on the baseball team?
Yes.
Well, go ahead. Who's on first?
Yes.
I mean the guy's name.
Who?
The guy playing first.
Who?
The guy playing first base.
Who?
The guy on first base.
Who is on first?
What are you asking me for? I don't know.
Wait a minute.
I'm asking you who's on first.
That's his name.
Well, go ahead and tell me.
Who?
The guy on first.
That's it. That's his name.
You ain't said nothing. I ain't asked you nothing.
You did.
You know the guy's name on first base?
Sure.
Well, tell me the guy's name on first base.
Who?
The guy playing first base.
Who is on first, Lou?
What are you asking me for?
Don't get excited. I'm saying who.
I'm asking you a simple question. Who's on first?
Yes.
Well, go ahead and tell me.
That's it.
That's who? I'm asking you, what's the guy's name on first base?
Oh, no. What's on second?
I'm not asking you who's on second.
Who's on first?
One base at a time.
Don't mix up my...
I'm not mixing up anybody. Now, what's the guy's name on first base?
Now, what is on second?
I'm not asking you who's on second.
Who is on first?
I don't know.
He's on third. We're not talking. Wait a minute. Whoa. Now, let's not...
Whoa.
Okay, I'll leave that there. But so this is the point where I ask, does anyone know what is the unit for power? What? I just asked, what's the unit for power? It's watts. Okay, so to help you remember which one is which, I find that a lot of people, I really try to drive home that energy is joules. And that is intuitive to people because you know when you talk about food, you might say, hey, a donut has 600 kilojoules, right? So I really want to remember that energy is the ability to do work. We know that energy is measured in joules. So that means power is going to be measured. What's power measured in? I just asked. What's the energy unit for power? What is the unit for power? Yeah. Anyway, but anyway, we really flogged that horse. Okay, so what we're going to go with is we have here power. The symbol is W. The unit is watt, named after James Watt. He was an early pioneer in the steam engine, and we have. He wasn't the first person, but he's the one who gets the thing named after him. And we have work energy, which are both measured in joules. Also, we use kilojoules. You also use kilojoules, obviously, and we also use kilowatt hours. Right, I'm going to talk about that in a second. Okay, so how I remember this, aside from trying to use the intuitive, what is the unit for power, and I would try to remind you that energy is the ability to do work. So energy is measured in kilojoules. If the donut has energy, it has 600 kilojoules of energy. Energy is the ability to do work, so work is measured in joules. How I also remember it's the rule of 1W. So that work is measured in joules, power is measured in watts. Yeah? We good? Okay. Moving on. So I think we've driven that home enough. And what we can see here is that 100 times 10 happens to be 1,000 watts. Yeah? Which if we use our pi formula, P equals IE, P, power, measured in watts, equals I, current, measured in amps, times E, measured in volts. Yeah? And let's have a look. So he explains what volts are, he explains what currents are, and then he says, well, what's W? What? Get it? Doesn't translate into Japanese. The work amount done per second is the flow of electric power. Yeah, the amount of work done per second is how much electricity is flowing, and power equals voltage times current. And then they show an electricity bill. Your electricity bill will probably not look like this, but they show that his electricity bill, the amount of power that he has used, not the amount of energy, the amount of oh wait, it is the amount of energy. Whoops. Okay, because it says watts, it's kilowatt hours. He's used 310 kilowatt hours. I wonder what the average Australian uses. Okay, while I'm looking at what does the average Australian use, what I want you to think about is how much do you think a PlayStation uses? How much energy does it use? want to take a guess?
1,000
1,000. What unit?
kilojoules.
Kilojoules. Okay. So I don't really want the energy equivalent. I want how many kilowatts per day is normal. Okay. So an average house in Australia consumes 80 kilowatts per day. 18 kilowatts per day. A light bulb. We at the start we talked about how an incandescent light bulb uses about 100 watts, or 60 to 100. I always bought 100-watt light bulbs, and these days we've replaced all of ours with LEDs. They use about 8 watts. Yeah, a PlayStation uses 200 watts. The air conditioner uses about 2,500 watts, or rather than saying 2,500 watts, we might say 2.5 kilowatts. Yeah, vacuum cleaners, they're measured in watts. And people, ironically, they want more watts. They don't see a vacuum cleaner and say, "Oh, I want one of them low energy vacuum cleaners." Everyone wants a high. People deliberately make their vacuum cleaners inefficient because they know that consumers, they buy vacuum cleaners based on how much energy they use. People want the 6,000-watt vacuum cleaner because it's a higher rating, and they always write it as 1,000 watts. They don't write it as kilowatts, because they want people to say, "Oh, 6,000 is a big number." Well, I mean, I think companies like Dyson's that use the batteries, they're not trying to sell that feature anymore. But if it's a plugged-in one, yeah, often they still are inefficient deliberately. Okay, so per day, so it depends. When we talk about the energy consumption, well, we're talking about, well, how many watts for how many hours did you use? We're turning this energy per second back into a total amount. So for every hour that you play the PlayStation, that's using 200 watts. And most Australians, well, they use about 18,000 watts in the day. So if we're saying that this is probably a quarterly bill, so it's going to be 90 days, 18 times 90. So Australians use about 16,000 kilowatts. I said 16,000. It's actually 1,600 kilowatts. And that is more than 5 times what this Japanese guy does. Now, that's probably because this is old, right? The energy consumption has increased. It's increased fairly dramatically. So this is, again, why climate change is a problem, is that we have so many devices. Everything, I look around, I can see so many things that are blinking. I can see fans that are left on. We just use a lot more energy. And because energy is so cheap, it's so cheap that if you live in a developed country like Australia, it's trivially cheap to pay for electricity. It's just a huge bargain. But also, Japanese homes are much smaller. They're better insulated typically. This is also one person rather than a household of 4 people. So those things all contribute. So where we say that Australia's power bill might be 5 times greater on average, the average household in Australia is probably, I'm not going to say twice as big as this guy, but it's I would say the average household in Australia is still substantially bigger. And then I would say that Australia is one of the worst. Australians use more energy per person than most people in the world. I think the US is slightly behind us. So worth noting. Okay, so the question is then, where does this electricity come from? Why is electricity consumption related to carbon change? Why do we care?
Because to make the electricity makes emissions.
Not in Japan, it doesn't. Do you see that symbol here?
That's nuclear.
Nuclear power plants.
It has yucky waste.
It has yucky waste. Okay, that's fair. It's fair to say that nuclear power plants have yucky waste. In the last year, I have kind of changed my mind on nuclear power. I will explain that in a second, but it's fair to say that nuclear power does still have some carbon dioxide associated with it. The uranium doesn't just jump out of the ground on its own. Yeah, we have to dig out the uranium. We have to transport the uranium. Those things all use a certain amount of energy, but it doesn't produce carbon dioxide by default. So the question is, well, and in Australia we don't use we sell nuclear energy. We have a nuclear reactor, but we don't have any nuclear power plants. And the reason we don't, well, we have moral opposition maybe to nuclear power plants. There's various reasons. Japan doesn't have a lot of access to resources. And it's a whole lot easier for Japan to be... So in the 70s, there was a oil crisis. Let me find you a video, a quick picture of the oil crisis. 70s oil... Okay, so the price of oil skyrocketed, and you can find some great pictures of what happened. So, petrol companies saying, sorry, no oil, no gas, gas shortage, sorry, no gas. Pump closed. You can see these long lines of people lining up to go to the only place anywhere that had petrol or gasoline, as we'd call it petrol in Australia. Would become very popular straight away, and there were just huge crowds of people trying to go to anywhere that could get access to fuel would become a huge hotspot. This changed car design. It made cars more efficient. So they reduced speed limits because reducing the speed limit makes cars more efficient. The cars got a lot smaller, and places like Japan said, you know what, we cannot be dependent on hostile countries for our energy supply. So what they said is, we don't have much uranium, but we trust the countries that make uranium, like Australia. We trust them a lot more than the oil-producing countries, the OPEC countries. And also, uranium can be transported much... So the amount of uranium that a household would produce in a year is smaller than the size of a can of Coke. Uranium, you only need a very, very, very small amount of uranium to produce a huge amount of electricity. Whereas on the other hand, if you said the amount of petrol, the amount of oil that you need to burn, well, we just saw actually a little while ago, the energy consumption per Australian household. Okay, so is that per year? Energy use per capita? I'm going to assume that's per year. Okay, so you're going to need 5 tons. Well, I don't know the density of oil, but for the sake of argument, yeah, 5 tons of oil, 5.5 tons of oil per person, right? So we said that a household produces about a Coke can size of uranium. It needs about a Coke can size of uranium, whereas you need 5 tons of oil per person. So a household of 4 people might need 22 tons of a ton is huge. A ton is what fits on the back of a truck. So the number of tons that you would need, it's 20 utes worth of 20 utes worth of fuel a year. So it's a lot of fuel to keep us ticking over. In Australia, we mostly get our fuel from coal, and coal does not burn clean. Or we can use natural gas, which burns a little bit cleaner. But the concept between nuclear power... so anyway, that's why Japan uses nuclear power. They did that for security reasons. But obviously the Fukushima earthquake and the resulting nuclear disaster, it has really hurt the popularity of nuclear power a lot. Now, before we talk about whether or not nuclear is good or bad, I have a video lined up ready to talk about that. All 3 of those systems rely on the same process for generating electricity. We said movement plus magnets equals electricity. Well, how do we generate the movement? Well, in all 3 of those examples, it doesn't matter if we're using oil, it doesn't matter if we're using gas, it doesn't matter if we're using coal, it doesn't matter if we're using nuclear power. All of those processes, it doesn't matter if we're burning rubbish, right? Some countries used to burn rubbish. I don't know if that's still very popular. Some countries burn dead trees and things, biomass they call that. I think that's lost popularity because it's even more polluting than look. I don't want to talk about areas that I'm not familiar with. All of those methods, they all work on burning something to produce heat, and then they use heat to make steam. So they heat up water, the water makes steam, the steam then turns turbines. Once we have the turbines are connected to magnets, movement plus magnets equals electricity. Works exactly the same concept as if I have Edison had a water wheel right, that he used from Niagara Falls. That's how he powered his electrical generators. Wind farms, well, wind turns the turbine. So the difference in those categories, all of those use generators, but some of those generators use natural or renewable methods of turning the turbine. It could be water, it could be tidal, right? It could be tidal forces, it could be air, wind, it could be water, it could be tidal forces. Or you can, you could generate steam by using nuclear power. Nuclear power creates heat, and that is how you can generate electricity. Okay, so let's have a look at what we've got here. So we can close who's on first, I don't know who's on second. Okay, so this is total generated is in picowatts. Now remember we've talked about the SI units. We've talked about how there's kilowatts. Well, power plants, they produce stuff in megawatts. They produce about 13,000 megawatts. Well, so another way of saying that is 1.3 gigawatts. Anyone who's ever seen Back to the Future, you both seen Back to the Future? Yeah. Yep. I think he needed 1.21 gigawatts of electricity to go back to the future, right? 1.21 gigawatts, right? 1.21 gigawatts is as much power. Let me have a look. Right. I thought I wrote that down. Yeah. Is as much power as a power plant produces.
How did he make that much power?
Well, he was using uranium. The whole plot was that he stole uranium from the Libyans because they wanted him to make a nuclear bomb, and he just gave them a whole bunch of pinball parts. And that's where there's the conflict at the start of the movie where they found me. I don't know how, but they found me. And I like that line. I use that line sometimes. Okay, so global production is not in gigawatts. It's not even in terawatts. It's the next one up, picowatts, right? And that's a lot of watts. Yeah. Well, I'm pretty sure pica is 10 to the 15. Because we're actually at a prefix that's so big that I don't even use it very often. Pica prefix. Pica is penta. That's what it is. I'm glad I checked it because I was saying the wrong thing. Pico is small. Penta. Petawatts, there you go. I still don't have how many that is. What is the magnitude of power? Kilo, mega, giga, tera, peta, 10 to the 15. Okay, the point is it's big. It's 1,000 times bigger than a terawatt. It's 1,000,000 times bigger than what a power plant produces. Okay, so if we go back to that post, electrical consumption is in pentawatts. So how many? It was 26 pentawatts. Okay, we can see that a big chunk of it is made out of coal. Another big chunk of it is made out of natural gas. And so they're both made from fossil fuels. Fossil fuels are made from dead trees, right? We talked about how in the Carboniferous era, there was too many trees. There was no bacteria that could break down trees. So when a tree fell down, it just stayed on the ground. Like at the moment, we have too much plastic, right? When we have plastic, it doesn't break down. But there is mealworm, so people are actually trying to genetically engineer objects that can eat plastic and get the energy out of them. Biofuels, 2% is still coming from biofuels. There you go, I take that back. Oil is the red sliver, that's 3%. And so most of this here is fossil fuels, right? Fossil fuels, there's only a finite amount of them. Now, here's my big reason why we need to move away from fossil fuels. Climate change is probably a huge concern for future generations. Every year I worry that it's going to be hot. Next year is going to be hotter than the last. It's summer right now, and even though we're in a La Nina year where it's raining all the time, it's just really muggy. And that's because increased temperatures mean that there's more water that holds in the air, which means that cyclones are going to be worse. It means flooding is going to be worse. It means that droughts are going to be worse. Now, there's lots of ways we can combat that, especially in developed countries, but in countries like the Maldives, where they're an island, that they have to worry about flooding and storms and just simply sea levels rising, or places like people like Bangladesh, where a lot of people live on the banks of rivers like the Ganges. I don't think the Ganges is in Bangladesh, but my geography is not perfect there. But the point is, that's a real problem for people. But fossil fuels are also really polluting. Fossil fuels have killed the burning of fossil fuels for energy. If you're burning 5 tons of coal per person, that's a lot of carbon dioxide that you're putting into the air, just polluting the air. The air quality is worse. The air quality causes respiratory problems. It causes asthma. It causes other health defects. It also is a finite resource. When it's gone forever. There's not going to be another Carboniferous era where we're going to just suddenly have a whole bunch of dead trees that are lying around that we can tap into. There's going to be a point where it's going to be too expensive to get that out of the ground, right? And when it's gone forever. So there could be a disaster. I mean, we've in 2020 was a mild pandemic, but we could have something like a comet hit the Earth, and you know what? We might not have access to solar power for 10 years. It'd be nice to have some saved up, fossil fuels in the ground that future generations could say, hey, you know what? Solar's not working at the moment. We might have to rely on other sources like fossil fuels. Save it for a rainy day. But Australia has taken the attitude that we just want to sell every last lump of coal that we can and sell it while there's still a market for it, because the world is increasingly saying no to coal. Overwhelmingly, the world is saying that the world is like banks, governments are increasingly setting laws to say that no new coal plants can be built, and they're increasingly moving away from coal because of global warming concerns. Okay, so let's have a look. What do we have here? Well, where's wind? Wind is the green sliver, which we can see. Wind is not much, but wind is growing. Solar is growing. Solar's growing at a big rate, but we can, roughly speaking, about 2/3 is coming from fossil fuels, and then about 1/6, is that right? Yeah, it's almost exactly 1/6 is coming from hydro, right? So hydro is pretty common. A lot of people are upset with hydro. So I often say that there's 4 things you need to know in this course. I say my first 3 things. You need to know concrete is made of cement and aggregates. You need to know that stress equals force over area. You need to know that steel has a yield stress of over 300. And then I say that the 4th thing that you should know is that the Snowy Mountains scheme, the Snowy Hydro project, is probably the biggest engineering project in Australian history. Just because if someone says to you, hey, do you know the Snowy Mountains scheme? And you're like, huh? Then you're going to sound a little silly as an engineer. So hydro, the Snowy Mountain scheme is a hydro electrical generation scheme. And a lot of people protested the Snowy Hydro scheme, and they've protested other hydro plants in Hobart. Even though they're renewable, even though they don't produce any carbon dioxide, they do disrupt waterways. And so people who want to protect habitats, I remember that there used to be this cartoon called Dot and the Kangaroo or Dot and the Koala. It was one of those two, where she went to Tasmania and she stopped the dam from being built. And by stopping the dam from being built, all the animals could be happy. I think these days, a lot of greenies would say, you know what, I think there's a middle ground where we can use a non-renewable form of electricity and still maintain habitats. These days, increasingly though, we're moving to wind and solar. These are the much bigger, these are the huge growth areas. The big thing is that solar, initially my view on nuclear was pretty pessimistic. And that was because about 10 years ago, I went to a conference put on by Engineers Australia where they talked about nuclear power. And they said, the problem is there's just simply not enough uranium for everybody. There's not enough uranium. And uranium fits that same problem of non-renewables. There's only so much of it. There's a finite amount of uranium, and there's not enough uranium for everybody. So us all moving to uranium, yes, it doesn't have any carbon dioxide emissions, and maybe it can be stored safely, maybe, but there's just not enough of it. There's not enough uranium for it to be a viable solution. It's too expensive and no one's going to buy it. That was before Fukushima. Okay, so subsequently, I think it was before Fukushima. It may have been after. I think Fukushima might have been 2008, and this probably would have been in about 2011. I was at this conference. But there has been big changes, particularly in the last 5 years. China really leading the way on this and this was sort of a twinkle in the that presenter's eye, was the idea of thorium reactors. So people have been talking about fusion forever. And there's this phrase that they talk about, which is called fusion never. So we're going to go back to our Scranton Watt picture. The electric city. They call it that because of the electricity. Okay, so I have a lot of stuff here where I talk about different forms of electrical generation and their environmental considerations and what I think about them. Okay, so we have nuclear. We have a reasonably good video essay by Vox. Vox is a media outlet talking about nuclear power. And the US uses a lot of nuclear power. And this is John Oliver talking about how badly nuclear is handled in America. The number of times that there have been near misses. And here is where a guy who just spent a lot of his time talking about nuclear power on Reddit. And so this is where you have to be worried about what's called astroturfing, where a paid employee goes onto websites like Reddit and then talks about what their company is producing and talks about all the positives without ever talking about any of the negatives. And it looks like it's just a regular person just sharing their opinion. But when someone's doing that all day, every day, you have to worry that maybe they're not being the most reliable presenter of information. Maybe they have an agenda. And so that's talking about astroturfing. Okay, so I have some stuff about renewals. I really want to focus on fusion never. So let's have a look if I can find that on the end of this big. Fusion is always 50 years away. And they call this concept fusion never. Okay, so back in the 1970s, there was a budget prediction in 1976 on how long it would take to get to fusion.